iLearner. Learn today, lead tomorrow.
It's kind of wild when you think about it, right?
Yeah.
Like half of the major industrial accidents in Europe, the ones where hazardous materials get released, it all boils down to the plants just being old.
Yeah, it's a huge issue, and not always in the headlines, but definitely under the surface. And for folks like you who want to stay informed efficiently, this deep dive into what the health and safety executive, the HSE, has to say about managing aging plant, this is going to be pure gold. Think of it as a shortcut to a critical but often overlooked part of industrial safety.
Absolutely. So we're cracking open this guide published by the HSE. The authors are P. Horrocks, D. Mansfield, K. Parker, J. Thompson, T. Atkinson, and J. Worsley. And this isn't just some academic paper gathering dust on a shelf. This is for the people in the trenches dealing with this stuff every day, industry pros and HSE inspectors. It breaks down how things fall apart over time and what can be done about it, drawing on real-life incidents where, well, things went wrong.
And that's exactly what we're aiming to do today, bring you those key insights. We'll unpack what aging plant really means, how widespread this problem is, and the different ways equipment can degrade, becoming a safety risk. Think of us as your guides through this dense but important topic. But remember, this is our take on the guide. The full document has loads more detail. Definitely worth a read. And we'd love to hear your thoughts and questions on our YouTube channel after you've had a chance to digest it all.
Perfect. So let's get down to brass tacks. When you hear aging plant, you might picture, rusty pipes and creaky machinery. But the HSE makes it clear that it's not just about age, is it?
No, not at all. It's way more nuanced than just how many years something's been running. The HSE defines aging as this process where a component's condition, how it's holding up, gets worse over time, making it more likely to fail. It's about wear and tear, the material itself changing as it operates and interacts with its environment.
So it's about how much it's deteriorated, not just how old it is. And they have a specific definition for aging equipment too, right?
Exactly. According to the guide, aging equipment is any equipment where there's either clear signs it's gotten significantly worse since it was brand new, or, and this is a big one, if there just isn't enough information to be sure about how much it's deteriorated. That lack of knowledge is a red flag in itself.
Makes sense. If you don't have the data to say it's fine, you got to assume it might not be. And the guide even mentions that new equipment can experience this, like accelerated aging.
Right. Absolutely. Things can cause even relatively new equipment to deteriorate faster than expected. Think about the specific chemicals it's handling, harsh operating conditions like crazy temperatures or pressures, even the environment outside can play a role.
So to sum it up, what's the HSE's big picture definition of aging plant we should keep in mind?
Basically, aging plant is anything that's no longer fully fit for its original purpose, or there's a strong chance it might not be. This could be because it's not structurally sound anymore, like the materials are weakening, or its function is compromised, meaning it can't do what it was designed to do reliably. It's not just about age, it's about condition.
Okay, that's a key distinction. Now, the guide goes on to list the different types of assets that can be affected by aging.
Yeah.
It's not just pipes and tanks, right? It's a much broader view.
Yeah, way broader. The HSE breaks it down into 4 main categories. First, you have your primary containment systems. This is the stuff directly holding the hazardous substances. Think pressure vessels, piping networks, those big storage tanks, the first line of defense against leaks and spills.
Right, the heart of the plant. And then you mentioned the control and mitigation measures. Those are basically safeguards.
Exactly. These systems are all about preventing accidents or limiting the damage if something does go wrong, like pressure relief valves, emergency shutdown systems that can quickly isolate parts of the plant, even fire water systems to fight fires. It's about having those layers of protection built in.
It's all about redundancy and backups.
What about the EC&I systems? That stands for electrical, control, and instrumentation, if I remember correctly. You got it. Now, you could lump these in with the safeguards, but the HSE pulls them out separately because they're so crucial. Think process control systems, alarms that alert operators, power supplies, backup generators. If those fail, it's a recipe for disaster. They're the brains of the operation.
Essential for safe operations. What's the final category?
Structures. This covers all the supporting elements that keep everything stable and safe. Foundations for equipment, bund walls, drainage to contain spills, access routes for people, even buildings housing key equipment. If any of those fail because of aging, it can have huge safety and environmental consequences.
So it's the whole shebang, really, not just the equipment itself, but everything around it that keeps it safe. When you look at it that way, the potential impact is massive. It's not just a theoretical risk either, is it?
Yeah.
How big of a problem is aging plant in the real world? Are we seeing actual consequences?
Oh, this is a real and present danger, no doubt. Chemical plants all over the UK and much of Europe are dealing with aging infrastructure. And this creates a whole bunch of challenges for operators, especially with global competition, tight budgets, and experienced workers retiring.
Yeah, that mix of economic pressure and a shrinking workforce sounds like a recipe for trouble when you add aging plant to the mix.
Definitely a cause for concern. That's why the HSE is so adamant that operators need to be proactive about identifying sites where aging poses the biggest risk. This means a thorough assessment that considers the inherent hazards of the site, how susceptible the equipment is to aging, the most likely ways it might degrade, and most importantly, how effective the current management strategies are.
So it's a very targeted risk assessment,
Yeah.
tailored to each individual site. To figure out the real-world impact, the HSE delved into incident data, right?
Yep, they turned to two main sources. Red Door, which is the UK's reporting system for injuries, diseases, and dangerous occurrences, and MARS, the major accident reporting system maintained by the EU. They wanted to see how often aging was a factor in these serious events.
And what did they find? How often does aging plant actually lead to accidents?
The MARS data was particularly eye-opening when it came to those major hazard loss of containment incidents, the really serious stuff. Their analysis showed that around 60% of those were linked to problems with technical integrity, and of those, a whopping 50% had aging as a contributing factor.
That's pretty alarming. Half of the technical failures that led to hazardous releases involve aging equipment. It really drives home that initial statistic we talked about.
It does, and the human and economic costs tied to those aging-related incidents in the MARS database were significant. From 1980 to 2006, they resulted in 11 deaths, 183 injuries, and over 170 million in economic damage. That's a hefty price to pay.
And the UK's RIDOR data, what did that show?
Based on their analysis, RIDOR suggested an estimated 173 loss of containment incidents between 1996 and 2008 that could be attributed to aging plant. But there's a caveat here. The guide points out that sometimes, because of reporting deadlines, the full root cause investigation isn't finished when the initial report is filed. That makes it hard to say for sure if aging was a major factor in every case.
So the actual number could be even higher than what's reported.
That's a real possibility, and it highlights how important those detailed investigations are. The HSE also noted that the level of detail in some accident databases can make it tough to pinpoint the exact aging mechanisms involved. This underlines the need for better data collection and analysis if we want to truly understand the impact of aging plant.
You can't fix what you don't understand, right?
Right.
So we've established that this is a big deal with serious consequences. Now let's dig into how this aging actually happens. The guide lays out some key aging mechanisms.
Right. This is where we get into the nitty-gritty of how things break down over time. The guide has this handy table, too, that summarizes the different mechanisms and, importantly, which types of assets they usually affect.
What are some of the most common or impactful ones they highlight?
Well, corrosion is the big one, so common and impactful, we'll dedicate some time to it specifically later. Then you've got stress corrosion cracking, where stress and a corrosive environment team up to cause cracks. Erosion, where a material is literally worn away by particles or fluids. Fatigue, which is failure from repeated stress cycles. And embrittlement, where a material becomes brittle and prone to fracturing.
So we're talking about materials breaking down on a microscopic level. But it's not just the materials themselves, right? External factors and the environment can also accelerate aging.
Absolutely. Things like physical damage from impacts or improper handling, spalling, where surfaces chip or flake, common in concrete and coatings. General weathering from the elements. Stress from repeated expansion and contraction due to temperature changes. All these contribute to degradation. And for instrumentation and control systems, you can see things like instrument drift, where the readings become inaccurate over time, dry joints in electronics causing intermittent failures, and detector poisoning, where sensors get less sensitive because of chemical exposure. Even ground subsidence can put stress on underground pipes and structures.
Wow, it's amazing how many ways things can go wrong over time.
Oh.
The guide also makes a point about the initial compatibility between the materials of the plant and the substances it handles, how that plays a huge role in how quickly things age.
That's a design consideration with huge long-term implications. If the chemicals are inherently aggressive towards the materials they're in contact with, you're going to see accelerated aging and degradation through all sorts of chemical reactions. It's like putting vinegar in a metal container, not a good combo.
Makes sense. So how does Table 3 the indicative guide to aiding plant degradation factor into all this?
Think of Table 3 as a tool for inspection teams. It gives them a rough idea of which combinations of process fluids and materials are most likely to experience aging, based mostly on how compatible they are. It's a risk-based screening tool to help them focus their efforts.
So it's a starting point to identify the most vulnerable areas.
Exactly. But the guide is very clear that this is just a general guide. It can't account for all the specific variables in a real plant, like those extreme temperatures or pressures we talked about. Those factors can have a big impact on how materials behave in the long run.
Sure. So you need the tables as a reference, but you also need real-world knowledge of the specific operating conditions to complete the picture. Now, let's dive into corrosion specifically. Why is it such a big deal when we talk about aging plant?
Well, corrosion is just everywhere, and it's a major economic drain. It's basically the deterioration of a material, usually a metal, due to a chemical reaction with its surroundings. Usually this happens on the surface where it comes into contact with a corrosive substance.
And there are different types of corrosion, right? Not just one catch-all term.
Right. You can broadly divide it into wet corrosion, also called aqueous corrosion, which needs water or moisture to occur. That's the most common type. And then there's dry corrosion or high-temperature corrosion. This happens at high temperatures, usually without any liquid water involved. It's more about direct chemical reactions between the metal and gases in the environment.
So water or no water is the main difference. What are some ways wet corrosion shows up in plants?
The guide outlines a few key mechanisms. First, you have general corrosion. This is when material is lost fairly evenly across the whole exposed surface, like when you see rust spread over a steel beam. This is typical with carbon and low alloy steels. You can monitor it by regularly measuring the wall thickness of components.
So it's a gradual thinning out over a large area. Now, localized corrosion sounds potentially more dangerous because it's concentrated in specific spots.
It can be, yeah. Localized corrosion is all about the attack being limited to small areas on the metal surface. This can lead to much faster failure compared to general corrosion, and it's harder to spot during routine inspections until it's already caused significant damage. Localized corrosion is often the main problem in those fancy corrosion-resistant alloys, but it can happen in carbon steels too.
And there are different types of localized corrosion, right?
Yes, a few important ones to remember. There's pitting corrosion, which forms tiny, often deep pits in the surface. It's sneaky because a lot of damage can occur below the surface with little visible evidence. Then you have crevice corrosion, which, like the name suggests, happens in tight spaces like under gaskets, washers, or loose bolts. These crevices trap fluid, creating a perfect little breeding ground for corrosion.
Yeah, finding corrosion in those hidden spots must be a nightmare.
You said it. Another type is galvanic corrosion. This occurs when two different metals in contact are exposed to a corrosive environment. One metal, the more active one, corrodes much faster, while the other might be protected. The relative surface areas of the two metals play a big role in how fast the corrosion happens. The guide specifically calls out corrosion at dissimilar welds as a prime example of this.
So where different metals are joined together, what other forms of localized corrosion does the guide mention?
We've got velocity-related corrosion, sometimes called erosion corrosion. This happens when high flow rates or turbulence in the fluid strip away the protective layer on the metal, exposing it to attack. Having solid particles in the fluid, like sand, makes it way worse. This is a common problem in copper pipes, but can affect other materials too. And lastly, there's mechanical damage, which can lead to cavitational corrosion. This is when collapsing bubbles in a liquid, often caused by sudden pressure drops, create shock waves that damage the protective layers on the metal surface. You'll often see this in areas with turbulent flow, like pump suctions, valve discharges, and those bends in pipes.
It's mind-boggling how many ways corrosion can happen depending on the specific conditions and the materials involved. The guide also talks about specific types of corrosion that are common in chemical plants because of the materials they handle, right?
Exactly. These are essential to understand in an industrial context. Carbon dioxide corrosion, sometimes called sweet corrosion in the oil and gas world, happens when CO2 dissolves in water, forming carbonic acid, which then attacks carbon steel. This usually leads to uniform thinning of the metal, but if the flow is fast, it can cause deep pitting. Then there's hydrogen sulfide corrosion, or sour corrosion. It forms an iron sulfide film on the metal surface, which can actually be somewhat protective in certain conditions, but if that film breaks, you can get really severe pitting. On top of that, hydrogen sulfide can also cause hydrogen damage in some steels, leading to things like blisters and cracks.
Those sound like the kind of corrosion that can cause major structural problems really quickly. And then there's the rather icky-sounding microbial corrosion that's caused by microorganisms, right, like bacteria.
That's the one. Microbiologically influenced corrosion, MIC, it's called. Basically, microorganisms like those sulfate-reducing bacteria, SRBs, get involved in the corrosion process. They create these corrosive microenvironments within biofilms that form on the inside of pipes, especially where water sits stagnant, like in those dead legs of piping systems or the bottom of tanks. They need specific conditions to thrive, though. You need the bacteria, a source of sulfate, a carbon source for energy, water, an oxygen-free environment, a near-neutral pH, and the right temperature and pressure.
So it's like a whole tiny ecosystem of corrosion happening right inside the plant. What about atmospheric corrosion, the last type mentioned in the guide?
Atmospheric corrosion is what happens to metal structures exposed to the open air. It's all about moisture, oxygen, and those nasty pollutants in the air like sulfates, nitrates, and chlorides. Basically, a thin layer of electrolyte forms on the metal, and the rate of corrosion depends heavily on how much humidity and pollution is in the air. For example, coastal areas with salty air have higher corrosion rates compared to dry inland areas, and industrial areas with more air pollution see faster corrosion than rural areas.
Makes sense. So with all these types of corrosion, what are some signs that operators and inspectors should be on the lookout for?
Well, the most obvious sign is seeing those corrosion products, rust, whether it's on the outside or during internal inspections. But the guide stresses a crucial point. Just because you see some rust doesn't mean the equipment's about to fall apart. It's a sign that aging is happening, but the key is how fast that corrosion is progressing.
So it's about monitoring the extent and the speed of the corrosion, not just its presence. What materials are usually most susceptible to corrosion?
Generally speaking, all metals can corrode under the right conditions. Of course, corrosion-resistant alloys, CRAs, are designed to be more resistant than standard steels because they form a protective oxide layer. However, that layer can get damaged by abrasion or harsh chemicals, making even those CRAs vulnerable to localized attack if the conditions are right.
So no material is totally immune then. What can plant operators actually do to manage corrosion risks in aging plant?
The guide outlines a few main strategies. Prevention is the best approach, and that usually involves protective coatings to shield the metal from its environment and cathodic protection systems. Cathodic protection can be done with impressed currents or those sacrificial anodes. If you've got these preventative measures in place, it's vital to have proof of regular inspections and maintenance of the coatings, plus ongoing monitoring of how well the cathodic protection is working.
And what if corrosion is already happening? You found it, what then?
Then it's all about monitoring and control. The guide breaks this down into 4 steps. First, you got to identify the high-risk areas through risk assessments and asset registers. Second, you got to actually detect the corrosion using visual and non-destructive testing methods. Third, you got to measure the damage, often by precisely measuring how much wall thickness is left. And finally, you got to assess what the corrosion means for the equipment's integrity and safe operation. The guide really emphasizes that any engineering judgments you make during this assessment have to be properly documented and justified. You need a paper trail.
That makes sense. You need to know where the risks are, find the corrosion, figure out how bad it is, and then make smart decisions about how to handle it. This has been a really eye-opening look into aging plant and the crazy number of ways, especially with corrosion, that things can degrade over time.
It really has. We covered a lot. What aging plant is, how common it is, the real-world impacts on safety and the economy, and all those different mechanisms that cause deterioration, with a special focus on the many phases of corrosion.
So the big takeaways are that aging plant isn't about a calendar date. It's about how much things have deteriorated and their increased likelihood of failing. And corrosion is a major player in that deterioration across many industries. Managing those risks effectively starts with understanding them, identifying them, and taking proactive steps to prevent or mitigate them.
Which leads us to a question for you, our listeners. Given how intertwined materials, environments, and operating conditions are in this whole aging process, how can industries create a culture of proactive asset integrity management? One that goes beyond just reacting to problems and instead anticipates, predicts, and prevents the effects of aging infrastructure. It's a real challenge.
Absolutely. And if you want to go even deeper, we urge you to check out the full HSE guide. Remember, what we've shared is our interpretation, our summary of that document. Reading it firsthand will give you a much richer understanding. And we'd love to hear your own experiences, thoughts, and questions about aging plant in the comments on our YouTube channel. Let's keep this conversation going.